Can you hear us now?
Yeah, we can hear you now. Thank you.
Okay, cool.
You have to summarize your introduction, okay?
That's fine. Okay, so you're gonna.
That's all right, you go.
Oh, that's fine, yeah. So, well, thanks for having me. I'm at the University of Oklahoma. And it's a pleasure to visit Gemini. I was observing at Keck on Monday night, and I took this opportunity to come and see some familiar and some new faces. So I'm gonna start with a picture of my group, and the reason I'm showing this is a lot of these people are actually using or have used Gemini, and I wanted to thank you for supporting our science indirectly, or without realizing it. I'm going to point out Grayson Jewett has an active Gemini program, and she's proposing for more in the next cycle. Manuel Barrientos had 2 Gemini programs, and he's proposing putting in another one. Adam Moss has published papers with Gemini data. He was an active user last time, and he's putting in more. So, expect to see these names. Also, we have an undergrad in the back, Megan, who used Gemini data for her capstone thesis. And then we have Aaron, who used Gemini data for his capstone thesis. I think that's it in this list. So, you have basically 5 grad and undergrad students, plus me, relying on Gemini to do what I do. So I appreciate, what you guys are doing. Okay, so I have one slide on, just remind us what a white dwarf is. And it's simply, okay, you go from a star, a sun-like star living for 10 billion years into a giant star that becomes 100 times bigger and lives for a little bit. And then, what happens to the planets? Are they still there? Do they survive? That's an interesting question. But then what happens beyond that is you have the core of the star that is left behind. It's the size of Earth. And because there's no nuclear fusion anymore, you end up with a star that is just cooling forever, essentially. In terms of the composition, most white dwarfs are about 0.6 solar masses. They are carbon-oxygen cores. They have also a helium layer on top of it, which is about 1% of solar mass. And then many of them also have a hydrogen layer on top that is 1% of the mass of the helium layer. So it's 10 to the minus 4 solar masses. So most of them appear to be these hydrogen atmosphere white dwarfs. So this is what stellar evolution does. Basically, this is Sirius and its dark companion. I like this image because basically what you have is you have a star like this, an A-type star, becoming that faint thing in the end. And here, even though the mass ratio is only 2 between the 2 stars, because the white dwarf is much smaller, right? It appears to be much fainter. So I alluded to white dwarf, or I asked the question, do planets survive? I'm going to show you some results from the Cycle 1 James Webb program, where we looked at 4 nearby white dwarfs to see if they have Jupiter-sized planets. Out of the 4, we have 2 candidates. And here we have on the left a 15 micron image from MIRI. And then this is what happens when you subtract a white dwarf. In this case, there's a source there. And then this is what happens if you subtract a candidate as well, trying to show that these are consistent with point sources. So we have 2 candidates. This one is about 10 AU away. This one's about 30 AU away. And they're consistent with being like Jupiter-sized objects. But we need more data. Well, we need follow-up to confirm that they're actually bound, that they're not just background galaxies, because we can't tell. But so we are putting in a cycle 3 proposal to hopefully confirm that they're moving together or not. So we'll see if they are real. But if they are, again, these would be survived planets, right? Planets that survived the stellar evolution. They are far enough away, right? So if it's 10 to 30 AU, imagine, or assuming that the star lost about half of its mass, they would have been closer. So I mean, it would have been like Jupiter's distance, at least the one on top, when it was the star was a main sequence star. So, and there are other surveys that are happening in cycle 2. There are 2 survey programs that are trying to image as many as they can with survey programs. We don't know how many they'll do in the end, but there are more programs trying to do this with a larger number of stars. So hopefully in the next couple of years, we'll detect some and confirm some of these Jupiter-sized trillion planets around white dwarfs. I think it'll be very interesting to see what they look like if we actually confirm them, try to do spectroscopy or to do multi-filter photometry to see what we can learn about these planets. So again, this is all preliminary because we haven't confirmed them yet, but it's very exciting and encouraging. Okay, that's all about James Webb I'm gonna talk to you about today because I want to focus on Gemini stuff that we have been doing. Here is a plot of what happens to a white dwarf as it evolves with time. So initially these stars are hot. So this is a plot of temperature versus density. So you're going from the surface to the center of the star. And I want to point out basically three things. One is where the star is degenerate. It's shown with these dots, where the density is like fluid-like density. So what is interesting is if you're looking at cooler and cooler objects, the density or the atmosphere that we see is actually very dense. We're getting close to fluid-like densities, like water densities. And then what is also interesting is if you look at the center of the star, as it cools down, it becomes a solid. So it actually crystallizes over time. So here's a video of what happens. We use this gamma parameter, which is ratio of the potential to kinetic energy. But basically, the star goes from what is shown on the left to what is shown on the right, and it creates a crystal structure as it cools. And then as it crystallizes, you have the latent heat of crystallization, which means that you have an extra heat source. So the star can appear younger longer. So it delays the cooling of the star. And then also the carbon and oxygen in the core, it separates. And because of that, you get extra gravitational energy release. And that can also delay the cooling of the star. So again, you may see them as younger. So on top, I have a graph showing the cooling of a cup of coffee. So somebody did an experiment where they took the lid off or they were holding the cup, so you get a little bit of a difference. So that's the difference between those blue and red and black lines on top. And then on the bottom, it's the cooling of a white dwarf. You can see it actually looks very similar. Obviously the bottom, the scale is different. It's, million years and temperatures are 1,000 degrees, but the shape is very similar because it's a similar process, right? We have a hot white dwarf with thermal energy and it's just cooling off over time. So this is what we have. And the nice thing is we can then use, if you then measure the temperature of a white dwarf, you know how it has been cooling, you can estimate its total age. Okay, so my talk mentioned, stellar, a revolution in stellar astrophysics, and that is Gaia. And this is an actual, this is not an actual video, but it's a video of if you take the Gaia data and if you multiply it, the astrometry, if you basically taking the proper motion and parallels it, if you multiply it by a large number, this is what it would look like. The actual constellations would actually appear to shift like that much, which I thought was an interesting video to think about. But I'm going to show you a map, not the sky map, but an Earth map from a while ago. It's a European world map, and I'm going to make a connection with Gaia. So in the sense that if you look at this map, what do we see is that we had a very good map of Europe in 1459. We know this was made by European because Europe looks really good, right? Everywhere else it's like not so good. But we know that we're also missing a lot, right? So that if you go to year 1525, now we see North and South America, but we just see the eastern shore, right? So now this actually, right, if you see this, then you're like, okay, what is on the west, right? There's curiosity, there's room for exploration. So the reason I'm using this is I'm going to go to another map, but now a sky map made also by Europeans, by Hipparcos mission. And this is the HR diagram from Hipparcos. And what you see is that we see these islands or continents of main sequence and red giants. But we know that we are missing some, right? We are missing basically stuff here. There are some white dwarfs there, but not much. So I'm going to compare this to the old map that we had. And then now with Gaia, we can actually see this missing continent of white dwarfs. Now, obviously, we knew white dwarfs before Gaia, right, we knew quite a bit of them from the Sloan Digital Sky Survey, but not like this, right? We didn't know the distances to a lot of them. There were parallax programs done at Naval Observatory. Sandy was part of a lot of that work, and those were limited to hundreds of targets. Now we actually have hundred thousands of white dwarfs that we know of. So now we actually have a way to explore this population for the first time, really in detail, to see what are the characteristics. And what is interesting is, if you look at this population in detail, it splits. It's not just one sequence. This was unexpected. Nobody expected this before we saw this. And we have this A sequence, A for hydrogen-rich atmosphere, and then B for helium-rich atmospheres, and then we have a Q for carbon. So we see this split, and so there's a lot of information there. So see what we can learn from this. What we did is we initiated a survey of the 100 parsec white dwarf sample using these different telescopes, including Gemini South. And soon after we started taking data, COVID hit, so Gemini South was closed, but we were still able to get data from Gemini South on about 30 targets, so it was still quite useful. So what we did is we looked at everything within the Sloan survey footprint and within 100 parsecs, hotter than 6,000 degrees Kelvin. And the reason for doing that is above 6,000 degrees, we can see hydrogen lines. So we can tell what the composition is. And if you don't see hydrogen lines, then you know that it's not a hydrogen-rich atmosphere. So here's how we do it. We basically have our spectrum at the bottom, and we are in the middle, we are showing one of the Balmer lines, if there is one, or the region around H beta or H alpha. And on top, we have the photometry shown as error bars. And then we have our models for hydrogen atmosphere white dwarfs, it's the filled dots. For helium, it's the open circles. Anyway, so what we do is we fit the photometry plus parallax, and then we get a model and we compare that to our spectrum. And the red line here shows what you expect for a hydrogen atmosphere white dwarf. And on the left, you can see that it fits in very nicely. So then we know this is a pure hydrogen atmosphere white dwarf. It's about 10,000 degrees and mass of 0.55. On the right-hand side, we have another target where you don't see any lines at all. You can see there's nothing in there, it's just a continuum. And fitting the photometry and Gaia parallax, if there's hydrogen, you would expect to see this feature from H alpha, which is absent. So now we know this is not a hydrogen atmosphere white dwarf, it's actually helium dominated. And we get these parameters at the bottom here. It's about 5,700 degree white dwarf, also about 0.55 solar masses. Then we have some DQ white dwarfs with molecular carbon. You see these huge, we call them swan bands from molecular carbon. So we fit it, and again, you can see what the temperature that we get, mass, and also the carbon abundance with respect to helium. And on the right, we have another example of a DZ white dwarf where you see metal lines from, in this case, calcium. Again, we fit them. So, this is just showing you the zoo of white dwarf spectra, the different spectral types. And in each case, we can fit the all of the available data to get parameters like temperature and mass and the composition. So our goal was to look at the mass distribution of white dwarfs, and this is what we got. So if you randomly pick a white dwarf in the solar neighborhood, it's most likely going to be 0.59 solar masses. You see this peak is very narrow. This is just fitting to Gaussians. What is interesting is there's this huge peak at about 0.6 solar masses. There's a shoulder, so the number of stars appears to be constant between 0.7 to 0.9 solar masses. And then there's a tail towards higher masses, and obviously we don't say anything about 1.4 solar masses, which they shouldn't exist, and we don't see them, so that's all good. We also see some very low mass white dwarfs, and these tend to be in binary systems. That's how we would form them, because otherwise there's no way to form a 0.2 solar mass white dwarf, given the age of the galaxy. So what we try to do is we try to explain this to see if we can explain the mass distribution based on single star evolution. So the red line here shows what you would expect to get, assuming constant star formation, an age of 10 billion years, then just take the population, make it evolve, use initial finite mass relations, and then you get a population of white dwarfs and see what that would look like. And because it's a single star evolution, you don't get anything below about 0.57 solar masses. That's because, again, given the age of the galaxy, you cannot produce these from single stars, so they must be from binary systems. But what is interesting is that we also do not predict a lot of these massive white dwarfs. So there's basically, you expect the number of massive white dwarfs to go down, but that's not what we're observing. So instead of going from 1D to a 2D mass distribution, here now we are looking at temperature versus mass. And what we have is, so these are all the observed systems, and different spectral types are shown with different symbols, but that really doesn't matter. What is interesting is if you look at this figure, we mark the blue line shows when the crystallization starts, and the second one shows where it occurred about 80%. So that's where you expect most of this latent heat from crystallization to kick in, which is an extra heat source. So it delays the cooling. So you can imagine your white dwarf starts on the left, it cools down, but then once it starts crystallizing, there's an extra heat source, which makes it slow down its evolution. So it spends more time between those blue lines. And so we see more of them. So this is direct evidence that these stars actually crystallize. They go through this crystallization. And these different lines show ages in giga-years of what you expect. But what is also interesting is you can see these, again, if you look at the models, they make this turn. So at some point, we also expect them to have the convective layer to reach down to the core. And that could bring up a lot of, or that could make the cooling much faster. So you expect them to cool really fast once they hit that. But we don't have a lot of stars to test that at this point. So this is basically direct evidence that crystallization occurs in white dwarfs, which is really neat. Now, the question is this what you expect from the current evolutionary models? And the answer is the models have issues. So on top, we have our data. So this is exactly like the previous one, but we cut our sample at 6,000 degrees because that's where we are mostly complete. And on the bottom is our model. This is based on population synthesis. Again, if you take a population of single stars, make it evolve and see what you expect from the white dwarf models. If you compare the two, there are two problems. We don't really see a pileup here because of crystallization in the models. And we see a lot of these cool and massive white dwarfs expected, whereas in the observational data, they're not there. So there's definitely problems. So we basically need another mechanism or an additional cooling delay, not just from crystallization, but maybe from something else to make them slow down even more. There are some ideas of that. And one idea is that in addition to carbon and oxygen, you also get neon-22 in the cores, and it could be like 1% or 1.5% or 2% of the core could be in neon-22. And so this idea was put forward by Simon Bluin about 2 years ago. And if you have a lot of neon-22, you could either create a neon-rich core or you could create a neon-rich shell. And that could also produce or provide an additional cooling delay, because whenever you move something gravitationally, there's the energy release from that. And he predicts that it could be for normal stars, well, for a shell, it could be like a 2 giga-year cooling delay for these objects. If it's a neon-rich core, it could be up to 9 giga-years, which is crazy. Right? So we don't know if this is really happening, but this is one way to provide an additional cooling delay to explain what we are seeing in our actual data. And what we are doing with Gemini, we have two tests that we're doing right now. The first one is we have a program to expand the sample down to 5,000 degrees. By doing that, we are basically, if you look at this plot, we expect average white dwarf at 0.6 solar mass to crystallize by that point. We want to see what exactly is happening down to that level. And also, we're getting into this convective coupling where the convective layer and the surface reaches down to the core. So we want to study both to see if we can understand what's really happening. So we have already taken all the data for that program from Gemini. It's under analysis. And the second one is, this is something that we are doing right now by my student Manuel Barrientos. And we are using wide binary systems where you have one white dwarf that is crystallized, another one that is not crystallized, to see, do you get the same age or do you get a different age? So we're trying to use those wide binaries to test what is the actual cooling age difference and critically constrain how much more do we need to explain this pileup from crystallization. So these are happening, as we speak. So hopefully we'll have those results out in the next couple of months. But again, this is all based on Gemini. All right. Another interesting thing that we did from this survey is looking at what we call ultra cool white dwarf. So this is Sandy has done a lot of great work on this topic, and it has been a puzzling topic, and it has been puzzling because what we have here is we have some stars that have photometry like this, energy distributions like this. What you are seeing is this is from pan stars. You see the star getting brighter and then fade very quickly. Here is our model. What you have here is what happens is as the white dwarfs cool, they form molecular hydrogen, and then you get collision in this absorption from molecular hydrogen. If it's a mixed atmosphere, you get collisions with helium. And so this is what is called the CIA opacity, collision in this absorption. And normally you would expect a cool object to peak in the infrared, but what this opacity is doing is it's mostly in the near infrared, and it's pushing the SCD, the energy distribution, to make it look very blue. Now, if you look at this fit, this is based on Gaia parallax and photometry. You see this star is supposed to be 2,700 degrees or so, and it's 0.09 solar masses, which is crazy. And this has been the problem for 20 years. The first of these objects was found in 1999, I think, or so. And this has been an issue since then. They appear to be really luminous and so really low mass, which is like, we don't know why. So what we did is looking at the Gaia HR diagram, there are some, the color scheme is not the best, but there's some magenta points that were the previously known of these ultra cool white dwarfs. So here we could identify additional systems. All of these red ones are Gemini targets. So we initially, once we saw this, we were like, there appears to be this additional sequence, which is really, we are seeing this for the first time as well. So we tested this with a fast turnaround program at Gemini. We looked at about 7 of those, and all of them turned out to be these ultra cool white dwarfs. So then we got more time to look at total 30. And it's beautiful data. So we basically, these are our Gemini spectra, and all of them basically are confirmed as these ultra cool or infrared faint white dwarfs. And a lot of them, if you look at these, they look really blue, and they don't have any lines at all. So they are what we call DC white dwarfs, but they're blue because of this additional opacity. And what also our collaborator, Pierre Bergeron, found that in his models, he was missing this high density correction to helium-free free opacity. And once he added that and then fitted our Gemini spectrum and the photometry, basically the black line is what we had previously, the older models. With the new models shown in red, now we can actually get decent or more normal parameters for these sources. So like this is instead of 3,000 degree, this is actually a 4,600 degree Kelvin, about 0.7 solar mass object with a mixed composition. So we're now getting much more reasonable mass estimates. And this work was done with including Sandy here as well. And it led to a follow-up cycle 2 James Webb program to look at in the mid-infrared to see what these objects are doing. We're observing 3 of them. So that's still data to come. But again, Gemini has been fundamental in discovering a large number of these stars. We tripled the number of these IR faint or ultra cool white dwarfs. And I don't want to say it's a definitely solved problem, but we've made a really big improvement or big progress on this field. Okay, another thing that we did with Gemini was the question of what is the most massive white dwarf, right? It's a good question to ask. Okay, we expect that there shouldn't be any above 1.4 solar masses, but can we actually find things that are close to it? So for that, it started with an email from Bergeron. He basically, looking at the Gaia HR diagram, he saw these three objects. And when he fitted the Gaia data, he was getting a mass above 1.45 solar masses, assuming hydrogen composition for this object and three others. And he sent me, this is copied from his email. He said, you know, anyone who has a telescope in their backyard, have three fascinating objects to observe. I said, we have Gemini, right? It's somewhat our backyard. So then we were able to get some DD time to observe these. And one of them turned out to be a DC white dwarf, so no features at all. It's all continuum. The other one is a DA white dwarf. And then we also did add, instead of Gaia, we added, in this case, some Galax data and Pan-STARRS data. And here we also have Sloan data, and fitting it, they turned out to be not as massive. They're not above 1.45, solar mass, whatever. They are more like this one is 1.33, the other one is like 1.3 solar mass. We're like, okay, then what? Well, then we said, okay, let's look at all of them that we could find that are above 1.3 solar masses. This is selection based on Gaia and Pan-STARRS colors. These lines show different models for white dwarfs. So going from 1.3 at the bottom to 0.6 would be like, right, going through the sequence. So we identified 25 stars that would be more massive than 1.3 solar masses, and this is for the 100 parsec sample. Among this sample, these are the most massive ones that we could find that have spectroscopy available in the literature. This is 1.34, that is 1.35 solar masses. So we do have white dwarfs up to 1.35 solar masses. One question is, did these actually come from single stars, or is it possible that they came from mergers? Now, the reason we ask that question is, if you look at the population synthesis predictions, this is from binary population synthesis, and you can ask the question of what fraction of white dwarfs at a given mass come from mergers. And now these are not just double white dwarf mergers. This could be merger during the previous evolution. It could be on the main sequence. It could be on, AGB plus a companion. So any merger that would happen in the past of these stars. And what you find is that so each curve shows you a different prediction, given that we don't know much about common envelope evolution, right? I mean, there's this alpha parameter. The question is how much of the orbital energy is used to lift or eject the envelope. It's a parameter that you can basically tweak. Based on that, it could go from, if you look at the most massive ones that we're interested in, it could go from 20% to 40% or so, based on these population synthesis models. Now, how can we tell if these stars that we found come from single stars or mergers? Now, Josiah Schwab made predictions on what happens if you have mergers. And what he found is that those should spin fast. And this is as a function of mass. He predicts rotation periods of like 5 to 20 minutes or so for these stars. Is that unusual for white dwarfs? It is unusual. If you look at, we have spin measurements for pulsating white dwarfs from Kepler and K2. Here's what you have. So most of them spin at about a day or so. So if you find something at, spinning at 20 minutes, it's probably a merger product. And interestingly, one of our 25 targets was discovered in 2020 to be spinning at close to 6-minute rotation period. This is based on photometry. So it has some kind of something on its surface that is causing this. It could be abundance variations. It's not known to be magnetic, but it's known to be a mixed atmosphere object. So something is causing that variation, but we know that it's spinning really fast. So at least we know one of them is spinning really fast. Another way to tell if the stars are from mergers is they may appear kinematically old. The idea here is that if you're looking at let's say binaries in the thick disk, let's say if they merge and create a single star that appears to be younger, right? They would have thick disk kinematics, but they would still appear to be young white dwarf. So this is the tangential velocity for our sample of 25 ultramassive white dwarfs, and we see 4 of them are 3 sigma off. compared to everything else. So we have 4 of them that are odd in terms of their kinematics. So we think that these come from mergers as well. And then they could also be magnetic. So there was work done by Briggs et al. In 2015, showing that what happens if you look at the mergers from different populations. So here you have AGB plus main sequence, or red giant plus white dwarf, etc. The predicted mass distribution appears similar to the observed mass distribution for magnetic white dwarf. So the idea here is that you create a magnetic dynamo during the merger process, and the star appears to be a magnetic white dwarf. So these are the different methods to find which ones of these stars are actually mergers. What we did is we had a program at Gemini to identify magnetic white dwarfs and rapidly spinning white dwarfs. So we had a spectroscopy program and the photometry program. What we found is that 40% of our targets are actually strongly magnetic. The way we find, which is crazy for a survey of white dwarfs. Normally, if you just do a random survey, it'll be about 10%. Here we have 40%, and the way we can tell it is, these are what happens to the Zeeman splitting of the Balmer lines as a function of field strength. So going from 10 to 100 megagauss. So we can see like this object is about 5 megagauss, and some of them here, we can't even tell because it's just a continuum. These lines are shifted so much that at some point we just get a continuum and we can't really tell what the field strength is, but we know it's like 100 megagauss or so. So anyway, these are our Gemini programs that we did. And so this is a really high number of magnetic systems in this ultramassive population. And then we had a program, we did some at APO, and then for the south, we used Gemini Zorro to observe. We tried to do all of the 25 that we could, and we found that 5 of them are rapidly rotating. Here, I show you the fastest one. This is from APO data. And what we did is we were looking at this system. We were doing photometry every 30 seconds. And normally we look at our sources for about 2 hours to see, to see if they're spinning fast and also constrain the period. I was bored after an hour, so I did a quick reduction and found this peak, which was it was less than our 4 sigma limit. And this is the phase folded one, but if it was real, this is really interesting. It's about 1200 cycles per day. So then I said, oh, let's decrease the exposure time and get more data, which is what we did. And soon after that, the instrument had some issues, and I'm like, we shouldn't have done that. We were able to come back and get more data the same night. And now you see this peak appear at about the same 1200 cycles per day at 5 sigma detection. Then we came back to it another night and found that it confirmed it. So this is spinning at 70 seconds. Okay. A white dwarf, this is 1.3 solar mass white dwarf spinning at 70 seconds, which is the fastest isolated white dwarf currently known. So then, combining all of this information together, we are basically looking at how many of them have large tangential velocities, how many of them are magnetic. You see a lot of them are magnetic, and how many of them are spinning fast. So we have like 5 that are spinning fast. If you combine all of them together, we find that 56% plus minus 10% of them are merger products, which is a really high number, right? So if you're looking at the most massive white dwarfs, more than half come from mergers and not from single stars. And here's our comparison to the population synthesis results. We only have one data point, but it is what it is. This is all we know at this point. And we have large error bars. But if you take that at face value, then we are saying we like this light green model better than everything else. And we can, we're like 3 sigma away from this line. So we want to do better, obviously. So we are doing it 2 ways. One is we extended the survey to all white dwarfs above 0.9 solar masses. So cutting out here within 100 parsecs. And we have done a survey at Gemini. We also used APO for the brighter ones. And this is all work that is done. So we're doing analysis right now to basically add more data points here to see, is it about 50% or is it actually less? So we can actually, for the first time, constrain what is the merger fraction as a function of white dwarf mass. And the second one that we are doing, also, again, this is also, we got some time some Gemini time in this cycle, and we're proposing to do more in the next cycle, is because our error bars are so large, because we were limited to 100 parsecs, now we want to go up to all of the Gaia white dwarfs that are more massive than 1.3 solar masses, do spectroscopy, see if they are magnetic, if they're, they're from mergers or not. So that's what we are putting in a proposal to do with Gemini in this coming cycle. Right, and another interesting thing that came up from this work is if you look at mass versus temperature diagram, one of these stars with this name shown in red appeared to be within the ZZ Ceti instability strip. That's where white dwarfs pulsate if they have hydrogen atmospheres. And these are all the previously known pulsating white dwarfs in the same diagram. You can see the previously known, the most massive ones were like 1.1 solar mass or so. If this pulsates, this will be the most massive one that is found today. Now, we originally got Gemini Zoro time to look at it, and this was the only target that Gemini couldn't look at that semester, which is, it's fake, right? But then we were able to observe it at APO on December 22nd of last year. Given that it's at -25 declination, it was really hard to do from APO. It's at air mass 2, but this is 2 hours of data from APO, and we saw 2 peaks. So in the Fourier transform, the original transform is shown in red, so you see 2 peaks, and then if you pre-whiten with the main peak, then the black shows what is left behind. So we saw something there, and I'm like, well, if this is really true, then this would be really great, right? It will be the most massive pulsating white dwarf known. So then I wrote a Gemini proposal the next day. My wife was mad at me because it was right before Christmas, and I asked for DD time, so I'm sure all people at Gemini were mad at me because it was before Christmas. But 4 days later, we got Gemini data, which is awesome, right? It's a very short turnaround time. And the data is beautiful. So we have data from 2 consecutive nights at Gemini South, and you can clearly see that this thing is varying quite a bit, and also the amplitude is changing, right? So there are 2 modes at least. And so in both nights, we detected 2 modes. Now it's not a lot of modes, but that is what the star is showing us at this point, given the baseline. And this is only like 45 minutes. This is I think about 70 minutes. But we confirm the star is pulsating. It becomes the most massive pulsating white dwarf currently known. And what is cool with pulsations is it's an independent method to constrain the parameters of the star, right? Astroseismology, we can do it with this object. With only 2 modes, it's not very easy. What we have here is the chi-square of each of these different models with different mass and different surface hydrogen layer thickness. So the mass goes from 1.22 to 1.29, and the hydrogen thickness goes from log of -6 to -10. So we have several models that give us really good fits. Again, because we have only 2 modes, we can't really tell which one is the best fit. Well, okay, we could say this one, but again, we don't want to do that. So we have some representative models that give us the mass. It's about 1.3, the temperature and the thickness of the surface layer. And also we get a crystallized mass fraction, which is about 99%. So this is a very cool system that, thanks to Gemini, we were able to confirm and publish. And we actually got follow-up time on UltraCam on October 5th of this year. We're going to look at this for 3 nights. I wish we could do it for Gemini, with Gemini for 3 nights, but I don't think anybody would give us that long of Gemini time to do it. But anyway, we're doing more follow-up on trying to constrain this system and do proper astroseismology of this system. Okay, so here are my conclusions. Just to remind ourselves what we talked about is we performed the largest ever volume limited spectroscopic survey of white dwarfs within 100 parsecs. And we are doing more with Gemini to extend that sample right now. And we found evidence of crystallization, and we found that the current evolutionary models have problems. They don't match exactly what we're seeing. We found 25 ultramassive white dwarfs within 100 parsecs, and we found that the most massive ones are about 1.35 solar masses. And a lot of these, well, more than half, come from binary evolution and not single stars. At least that's what we were seeing in terms of magnetism, rotation, fast rotation, or kinematics. And we could use that to say something about common envelope efficiency, but I think it's still too early to really say exactly, what we prefer. But we're getting more Gemini data to really nail that down and compare with binary population synthesis results. And in the future, things are getting better because we have LSSD and we have these spectroscopic surveys that are targeting, specifically looking at or getting spectroscopy of a large number of white dwarfs. So in the next decade, we should have a spectrum of every white dwarf that we know of from Gaia. And I'll finish by saying that Gemini has been really fundamental for my group's research. So I thank you all for that. And I'll take questions.
Yeah. Questions online?
Yeah.
Okay. In the most massive one, couple slides back, the parallax, the distance is not known for that guy, because in your in that table you had a list of distances.
Right. It is the distance is known from Gaia. This is the distance that you get from the astroseismology model, because it gives you an independent estimate.
Mm-hmm.
Now, so yes, based on that, we could say, I forget what the distance is exactly for this object. It's within 100 parsecs, it's not going to be, that. So we didn't use that to really say much because we only have 2 modes. So we don't want to make too much of that and say this is, this is the best solution yet. But we can definitely use that in our final analysis with more follow-up data. To choose, what is the best astroseismological model,
I have a really stupid question to show my ignorance on the field. When you show the map of Gaia with the HR diagram, above the white dwarf, there are like 5 or 10 little clumps of other stars. It's until when you show them.
Okay, like
that. Yeah.
Like here?
Yeah, with the one with the visual luminosity of 5. Yeah, you were there.
Hold on. No, I went too far. Sorry. Like this one?
Yeah, on the right side, on the top, up. You go up the white dwarf, and there is this clump.
Oh, that?
Yeah. There was nothing in parkour, so no clue.
Right. Okay. No, that's a very good question. So we know that these ones are white dwarf plus M dwarf pair. So that's where you get them. So those could be subdwarfs, subdwarf B stars or so.
So it's not a continuation of the.
No, it's not a continuation of the white dwarfs. No, I mean, the white dwarf sequence is like here mostly. Yeah.
The blue variables. Anyway.
I think they're probably given the magnitudes, I think they're probably subdwarf B stars. I guess,
Could you show the other HR diagram for the later on?
Like this one?
Yeah, just that one you can really see the split between the the hydrogen, the helium, and the DQs. So it's nice.
Yeah.
The two solid black lines, and then the little piece going off to the left.
Yeah. So I mean, this over density is it's consistent with that crystallization, making things stay bright longer. Because if you look at the models actually don't match the cooler end right there below, but crystallization can make them appear brighter. So, I mean, this is to say there's still a lot of problems really matching, especially for the cool white dwarfs, considering their parameters and getting their ages.
I have another question.
Yeah.
Shows that they don't.
No, I mean, this is all good stuff. Yeah.
Well, when you try to get the temperature, you are like some of the generated radius of the star. Are these objects too small to be resolved with Chara or any?
Yeah, no, there's no
no way to do.
Yeah, no, we can't resolve. But because we know the distance, right, you can constrain the radius of the star given the photometer that you have, right? And then once you know the radius, then you can use a mass radius relationship to estimate the mass.
You're not concerned about that. You get it some other.
I mean, we get it using guided parallax, which is precise, right, for these objects that are nearby. Yeah. Yeah, but yeah, resolving the surface, no, that's not going to happen. Yeah. Wow.
They're the size of the Earth, so
Yeah.
they're, yeah, well, maybe, yeah. Another question too, but anyone would know. The plot of the binary fraction and the different models. So the top line, you said that's inefficient common envelope. I didn't quite understand.
Right. So inefficient, meaning that, okay, when you have the stars go through binary, the common envelope, what fraction of that energy is used to eject the envelope? So if it's inefficient, then it's not very efficient of getting rid of the envelope. So then you end up with more stars merging. And if it's efficient, it's an efficient process, then you can eject the envelope easier, and then those stars don't merge. They survive the common envelope evolution. So that's why if it's inefficient, you get a larger fraction of mergers and larger fraction of these massive white dwarfs coming from mergers. And we are finding that that is what we are seeing for the most massive white dwarfs at this point.
I have a more simple question then.
No, yeah, go ahead.
Because I don't know anything about this. So I'm curious about when you say you're looking for the fastest spinning merger products.
Yeah.
How the spin period starts? They started out spinning fast, and then over 100 million years they just slowed down. Were you able to backtrack when they could have merged?
Well, I don't think so. I don't think we could. Yeah, because I mean, in this case, we don't know the initial spin rate to begin with, right? So you could assume, okay, if you believe these calculations, then you could assume an initial spin rate, but for our star, it's 70 seconds, and it's not even predicted in these models. So, right, it's I don't think that's possible.
Interesting though, worth pursuing that, see if you can trace back the tangential velocity or the spin or something.
Yeah.
And for the low mass objects that have to be mergers pretty much, anything below 0.5?
Yeah, so anything below 0.5 should come from binary systems, not mergers, but binaries that, and if you look at the lowest mass ones, if you look at below 0.3 solar masses, 100% are in binary systems. We actually see the companions, we see velocity shifts of extended periods, and we have found things down to like 10-minute periods. If you look at 0.4, 0.5 solar masses, most of them are in binary systems as well, about 70%. There are some that are single. It's not clear why they're single. There's one idea that maybe you could have a binary evolution of the brown dwarf that evaporates, so you just don't see it. You end up with a single star. or maybe the star is so metal rich that you get extra mass loss. That could also create the single very low mass white dwarfs, but at least for the general population, yeah, you need binary evolution to explain anything less than like half a solar mass.
And in that case, you got two very different objects and exchanging mass.
Yeah. I mean, you have common envelope evolution for some of them, or it could be stable mass transfer as well. Yeah, two like short period binary. Well, two stars in short period binary. Yeah.
Remind us of the Chandrasekhar limit. It's the
1.4.
Yeah,
1.4, yeah.
1.4, yeah. I mean, people have looked at going from like single star evolution, what is really the limit? And I think it's more like 1.38 solar masses or so, but
Oh, sorry, go ahead. Do you think if there's possibility for future gravitational waves, for you to see like gravitational waves from binary members?
definitely. Well, so we know of some verification binaries for LISA. So some of these, 10-minute period binaries, double white dwarfs, so they're definitely going to be seen by LISA. The number is right now, I think like 30 or so that are known. But the predictions is that there should be like thousands of them in the galaxy, and binary white dwarfs are going to be the dominant source in LISA. Actually, LISA is going to find a lot of those, and then a little bit of the exciting stuff that people talk about, MREs and everything else, right? But that's the main contaminating source in LISA bands, really, which is good for us because then you'll find all of these double white dwarfs in the galaxy.
If the limit of the real limit of the Chandrasekhar mass is 1.38, aren't you surprised that everything that you find above 1.2 is actually a merger? Shouldn't be some random star?
Yeah, well, we're not saying everything is a merger, right? We are saying like 56%, yeah. So yeah, I mean, there should be some single stars in there, yeah. Well, thank you all.
thank you.
Yeah, well,
Thank you very
thank-
much.